This particular talk has me switching between like 4 virtual desktops, so it can get a little bit confusing. There's lots of switching around for me to do in the background, but for you, it should be pretty seamless. But yeah, this is a talk about how I went about building a Raspberry Pi based robot arm that's controlled with .NET 5, C# to be specific, and Blazor and SignalR and a few other things on top of that. Yeah, thanks for coming along to that. I'll also just get my chat open over here so that I can see what's going on and move on. So a little bit about me. I tend to be one of these people that just doesn't sleep, apparently, so I do a whole heap of things. So I'm a Microsoft Azure MVP, I'm a Microsoft certified trainer, Pluralsight Author, public speaker, Meetup organiser, and I've got a family with a couple of young girls at home as well. So I'm personally driven to help young people and into the area of STEM and stuff like that. So being a code club organizer and a STEM ambassador helps me with that. So what we're going to do tonight, we're going to look briefly at .NET 5. Being a .NET group, I'm hoping that you would know a bit about that, but we won't linger around on that too much. And then we'll look at what's involved in getting .NET installed on a Raspberry Pi. And then we'll spin up some various different Hello World projects. And we'll look at the Raspberry Pi GPIO and the circuit that I've got over here. And then we'll talk a little bit about how we can control GPIO with .NET. And look at device bindings and how then we can drive servos and how they work. And then we'll move on to Blazor and SignalR for some fun, and then some final demos after that, and then some Q&A. So onwards from that, .NET 5 is cross-platform and allows us to be able to program in pretty much any language we like and target any platform we like, all the way from desktop through to AI, and over there on the right-hand side, handily for us, is IoT, which is where we'll be spending most of our time. So yeah, open source and cross-platform, including the Pi, which is nice. And with that, we get the latest C#9 language features, including records and init-only properties, where we start out with something like that and we drop it down to just a few lines of code. Pattern matching, which is quite nice. I quite like that, matching on patterns. Top-level programs, where we start out with already quite a small application, but we can drop that down to a couple of lines, which is fantastic for people picking the language up for the first time. System.text.json, which of course makes James Newton King a little bit unhappy because we no longer need his Newtonsoft JSON library. There's quite a few words on this particular screen, and this was at last year's build, not even this year's build. But the one I like is the bottom right-hand corner, where 40% new .NET developers are students, which I found quite a surprising revelation there, and something I really like, because obviously colleges and universities would normally be C++ or Python and things like that. So it's good to see .NET finding its way through that university feeding system into obviously companies after that. So getting .NET installed on a Raspberry Pi ordinarily would be quite difficult, but I've created a single line install script for that. By the way, I'll be sharing the link to the slides at the end of this, so don't worry too much about copying any of this down or taking screenshots. But you can see in the GIF at the bottom of the screen there, sort of all the steps that you'd have to go through manually. And if you're not a massive Linux person, then you might find some of that a little bit daunting. And even if you are a regular Linux person, there's just more steps than you need to be going through. It would be nice if there was a sudo apt-get install for .NET 5, but for the Raspberry Pi, there just isn't. I think there is for Ubuntu and things like that, but not for Raspberry Pi OS. So that's what that particular line will let you do. So once you've done that, then you'll be able to spin up a console app. And what I've got across here is my Raspberry Pi. And if I do a .NET --info, and obviously let me know if the text is too small at any point. But we can see here my Raspberry Pi has got version 5.0.202 of the .NET 5 SDK on there. I think that's a little bit out of date just because of how long it is since I've installed it. But should I just run that install script again, it'll give me the latest version. out of the box. I just don't want to break the demo just in case something's broken. And once you've done that, of course, then you can do a .NET new console and then do hello world. And that finish. Oh, what? .NET new. Oh, yeah, that should have worked. Oh, I know why. Let's do this, shall we? Try that again. There we go. Helps if you're in the right directory when you start something out like that. And go into that, and then we can do a .NET run. And we'll get hello world. And now you can see, obviously, the Raspberry Pi I'm using is a Raspberry Pi 4, actually. And although it's a beast of a machine for how small it is, it's not going to be the equivalent of your desktop machine. And I don't think that .NET on the Raspberry Pi is multi-threaded or anything like that at the moment. It's pretty standard stuff, but it works, and it works fast enough to be able to do this sort of IoT bits and bobs that we want to be able to do. So this is always a good thing to do once you've got this installed, just to make sure that you've sense checked yourself, it's all installed properly. Even just forgetting to reboot it after you've installed it can have little problems that aren't as obvious as you'd imagine them to be. So that's that little bit. And get my slides back. There we go. So now that we've done that, it's a bit boring just doing hello world. We need to actually make something happen. So to do that, we can use what's called the GPIO on the Raspberry Pi. And GPIO stands for General Purpose Input Output. And that's all the little pins on the edge of the Raspberry Pi there. And all of these pins support basic I/O, as well as things like serial interfaces, SPI, I2C, and also PWM, which is nice because that's what we're going to use to drive our servos. And I'll talk about that in a bit more detail in a bit. It's this particular NuGet package, system.device.gpio, is the one we're going to use. And that supports Raspberry Pi, but also other boards like BeagleBoard and Hummingboard and Odroid that I've just never used. I've never really seen the point. I'm a big Raspberry Pi fan, so I tend to stick to that. It supports Linux and Windows 10 IoT. Now, I don't recommend people use Windows 10 IoT anymore. That specific brand of Windows that I'm talking about there is this cut down Raspberry Pi flavor that will let you run XAML apps, essentially. But there's no real need to do that with things like the Uno platform giving you native XAML, essentially. For the Raspberry Pi, is just no need to corner yourself with Windows 10 IoT. Easy to install, just the same as any other package with the CLI or the NuGet package manager. So to talk about GPIO a little bit more, as I said, there are all the pins down the side of the Raspberry Pi. And on there we have various different things. Here we've got power, and we've also got TX and RX for a serial port, the PWM there, and then on the left we've got various other pieces of I/O. It's interesting at this point, and we'll see this in the code, that there are two different numbering schemes that you can see. So these numbers here closest to the pins is what's called the board numbering scheme. And then there's also this BCM numbering scheme, which is referencing the I/O chip that drives the GPIO. And I recommend that you don't use that numbering scheme, because then you're having to convert from one numbering scheme back to the pins. We can all count the pins on the Pi, so long as you can see that square pin in the top left is pin 1. And then next to it is pin 2, and beneath it pin 3 and pin 4 and onwards. So once you know that, counting the pins is easy. Losing count is hard, but you can count them. It's fine. Count backwards from 40 if you need to. So the circuit that we'll start out with is the hello world of IoT. And that is to flash an LED, and after that to read a button and flash an LED. This is just what you tend to do with any basic IoT stuff. So it's a good place to start. So what I've got here is an LED, a button, and a resistor. So I've got one side of the LED connected to pin 10, and that goes through the resistor and then back down to ground to make that circuit, so I can flash the LED. And then I've got one side of a button here connected to pin 26. And you'll notice here that there's only one resistor. And if you know a little bit about electronics, you might be asking yourself why I've not got what's called a pull-up resistor on the button. Well, the Raspberry Pi has got the facility to do this pull-up internally. It has some weak pull-ups that you can turn on for various different pins on the Pi. So that's what I'll be utilizing. And again, we'll see that in the code in a bit. So let's do that hello world, but with the LED and the resistor. Now, the reason why I've got this on the screen, you can see, is because you'll then be able to see the LED flashing, and actually it'll be over here. So I sort of angle that over this way a little bit, and you might be able to see it a little bit better, but I'll move it when it comes into shot anyway. I've actually got another demo wired up as well for smart home stuff, so that's what that socket's doing over there, but you'll be able to see that LED flashing anyway. So I'm not crazy enough to do a whole heap of live coding. So I've got a GitHub repo for all of this, and all of the steps are all branched out. And again, the code will be linked to in the slides later, so don't worry too much about that. I'll briefly go through the code, and again, a shout or oh yeah, what OS did Pete say is running on the Pi? Yeah, Raspberry Pi OS as it's called now, Raspbian. As it used to be called. In fact, when you do that .NET-info, it still says Raspbian in there. So that's what that is. And I'm running the 32-bit version, by the way. It's worth noting that my scripts only support the 32-bit version because they do. I've just not had time to make the 64-bit versions. They are coming, though. So the code, that's that system.device.gpio, which is going to do all of the heavy lifting for our inputs and output stuff that we're doing, our GPIO control. So we're bringing that in. And then I always leave this hello world line on here, because if your LED doesn't start flashing and your code's not doing anything, sometimes you don't even know if it's finished starting up. Certainly as the Pi can take it a little bit of a while to do that. So I always just leave that in, and I know the thing's started. So next up down here on line 14, we have this GPIO controller we're creating. And you can see here we're passing in a pin numbering scheme of board. So we could have chosen BCM if we wanted to, but as I say, I recommend using board for that. So we create one of those. And then I've got a couple of variables here. So I've got the pin number, and if you remember, I've got my LED connected to pin 10. And then I've got a variable that's going to hold a value in milliseconds, essentially. And we'll see that in a second, but that's going to help me with the timing for the flashing. And then I take my controller that I've created above, and then I'm calling the open pin function, and I'm passing in my LED pin, and I'm setting that pin mode to be an output because I'm going to drive the LED. And then here in a loop, all I'm doing is I'm writing to that pin a value of high, and then I'm waiting my light time, 300 milliseconds, and I'm writing a value of low. So high will turn the LED on, and low will turn the LED off. And then I wait again and go back around a loop. And at the end, I just close the pin, just because that's, something good you can do to make sure that you release all of those resources. So let's just have a look at how that's working. So I'm going to drag this to one side and get that over there so that you can see what's going on. And if I do robot and then firmware and then run that, assuming everything is still working, then we should get a flashing LED. I don't think, if I do that, then we should get a better view. There you go. So you should be able to see that LED flashing nicely in there now. So, I mean, that is the first thing that people tend to want to do is flash an LED. The Raspberry Pi, of course, doesn't have an inbuilt LED. So if you've ever done something like an ESP8266 or something, a lot of these boards will have an LED built into the board, which is nice. And I actually asked Eben Upton directly why he didn't put an LED on there. And he said, well, because somebody might want that I/O pin. And if I've got an LED connected to it, then they can't use it. So there was a good reason for not doing it. And it probably took 1p off of the cost of the Pi, and at the time they were trying quite hard to make sure that they kept that cost down. So that's what that's about. So that's that piece of code, but obviously we've proven that we can drive the outputs rather of the Raspberry Pi. The next thing we want to do is make sure that we can read the inputs. So I can switch to the next branch, read button. And then I'll just quickly go through what the code's doing. Again, we've still got this system.device.gpio, as you'd imagine. And we're still using my little it is starting up hint here. I've added in a variable for our button pin. And if you remember, that was connected to pin 26 on the Pi. And then I'm still opening the LED as an output here. And now I'm opening a button pin as an input, and I'm doing that input pull-up. So that's turning on this internal resistor that's going to make sure that if the button isn't pressed, that it sits there at a high level. Now, what this is doing, of course, is it's going to make the logic a little bit backwards, because if I'm not pressing the button, then the button is going to be reading as high as a 1, as true. And when I do press the button, the other side's connected down to ground, to 0 volts. So then it'll read low, false, 0 at that point. So the code down here makes sense now that you know that, essentially. So if I read the button and it's false, then I turn the LED on. So it's kind of backwards what it's doing. And if I don't press the button, so it's reading as a high value, pulled up by that internal pull-up resistor, then I can turn the LED off. And then I'm closing that output pin again there, just to tidy things up again. So let's have a look at that in action. Let's start it up. And then get my thing on the screen. Yeah, that's started. And now if I press the button, then we have quite a long-winded and reasonably expensive way to connect a button to an LED. I could just wire the wires directly to it, but as you can see, that is now reading the state of that button and then setting our LED on. And this is great now because we've got control over the inputs and the outputs, and GPIO is at our mercy at that point. We can do what we like, but there are other things we can do. So if I switch back now to my slides, this device bindings will let us control things like temperature and humidity sensors, which is often the next step that people will take in IoT projects. And I know my good friend Cliff Aegis, who's a pilot for BA, but on the side he does a lot of IoT work, and he and I run a Twitch channel together, a Twitch show called IoT Live, and we'll often laugh to each other about this temperature and humidity. You look at any of the docs around stuff, and it nearly always uses temperature and humidity as the example, because you can get constant changing data. But yeah, it'd be nice for people to think outside the box a little. But what's great about this IoT device bindings NuGet package, and this isn't the system.device.gpio, this is a different NuGet package, is that there's a whole heap of somebody else's code here that drives a load of peripherals, including IO expanders, Explorer hat, which is a Pi hat, the Sense hat, which, if you didn't realize, there's 2 Raspberry Pis in space taken up by Tim Peake's mission. And they've got this Sense hat on there, which has got temperature and humidity sensor, of course, but also a magnetometer and a display and a couple of buttons and a gyroscope. And what those 2 Raspberry Pis are letting people do is that students in classrooms can write code against it in Python as it happens and run experiments in space, which is a fantastic way to get young people interested in STEM subjects. If you can tell them it's running in space, then their eyes light up. So that's great. But onwards from that, what's good for us is that there is servo control within this IoT device bindings, which means that the act of controlling the servo is just so much easier. And I'll come back to the reason why that is shortly. But the circuit now grows because what I want to do is control this robot arm. So down here at the bottom, I've got the Raspberry Pi hooked up to something called a Servo 6 control board. Now, I don't necessarily need this, but what you can't do is hook a bunch of these servos up, and they're like mini motors. You can't hook them directly up to the Raspberry Pi because there's just too much current draw. Those things, when they start up, will take a surge current that can, if you're unlucky, just brown out your Raspberry Pi and reset it. And if you're really unlucky, it can kill the GPIO pins on your Pi. So this board essentially splits out the power and the control. So what I've got down here is the control lines connected into the board. It's a little bit confusing, but actually that first pin on the right-hand side there is ground, and I've got that connected to pin 25, which is ground on the Pi. And then over here on pin 35, I've got my first servo control pin, and on pin 13, I've got my second servo control pin, and then on pin 12, I've got my third. Now, what's interesting is the Raspberry Pi has only got 2 what's called hardware PWM ports. So that third one is going to be using software PWM, and I'll come back to that in a bit. Down at the bottom, we've got the servos connected down here, and these servo control wire colors are pretty standard. There's two different ones, either ones that you can see here that are yellow, red, and black, or you can have ones that are orange, red, and brown. And the orange or the yellow wire here will always be the control wire. So if you can just stick that, and it's very hard to see, but on the far left you can see a little tiny C above that yellow pin. So that'll be the control. You can't blow anything up much if you plug them in the wrong way anyway. It just won't work. So yeah, control there on the far left, and then power, and then ground. So servos, they are, as I say, that they're like a little mini motor, but they're a bit more constrained than that. And they're driven by something called PWM, which is pulse width modulation. So what you can do is, if you think about it like this, if you've got a narrow little pulse with a big gap in between it, it'll go one way. If you've got not so narrow pulse with not so big a gap in between it, it'll go to the middle. And then a big long pulse with a little gap in between those pulses, and it'll go the other way. So we are varying the width of those pulses to be able to set the position of that particular motor, or servo as it actually called. Now, I've got 3 of these connected to my robot arm, and I've got one that rotates the robot arm. I've got another that moves it sort of in and out or reaches, and another one that's got a pair of pincers on it, and you probably saw some of that without it moving when I was demoing the LEDs. So that's what my 3 LEDs are doing, 3 controls are doing there, 3 PWM controls are doing. So we'll start here with just moving the servos around, and you should see then our little robot arm moving. So I stop this code and go back to here and switch to the next branch. We can move the servos. And I'll just quickly go through the code here. So we've still got GPIO, but what I've added here is PWM and PWM drivers. That actually comes from the system.device.gpio NuGet package there. So you can see PWM and PWM drivers coming from that, but we've also got the IoT.device.servo motor NuGet package, so or section from the NuGet package. So that's the one that's coming from the device bindings library. So PWM built into that GPIO library we had before, but the ability to control a servo motor using PWM is somebody else's code that we're using here. So that's what I've made use of. So down here we create this PWM channel from the GPIO library, and we pass in some parameters here. So this first one is the chip number. And there's only one PWM chip on the Pi, so both of these are 0. Then you pass in the channel, and there's only 2 on the Pi, so we've got a 0 and a 1. And then we pass in a frequency, and I've just left that at 50. Next, we create a servo motor from them device bindings, and we pass in the PWM. And then we set the maximum angle. Now I've got 180-degree servos. If you imagine, for the most part, a robot arm will only really want to move 180 degrees or there or thereabouts. If you'd made that reach go 360, well, you'd be digging your desk up. And then we've got a minimum and a maximum pulse width here as well. Now, I've just got really cheap 9G servos that I bought from Amazon, and the next lot you get might be slightly differently calibrated. And so these 3 figures will let you calibrate that slightly better to be able to make sure that it moves in the same way as the other ones you've got. Could be quite important, but in my case, doesn't really matter. So I kind of just settled on these 2 figures. I think that was the figures that the demo code had even. Now, next down here, as I said, there's only 2 hardware PWM channels, but in the device bindings library, we have the facility to be able to create a software PWM channel. So you imagine that to get the servo to move to a particular angle, you've got to get that pulse width to be the same every single time. So this is actually quite a difficult thing for the Pi to do, because you've got an operating system in the way. So actually precise timing is difficult. But luckily somebody has figured that out. So we've got the pin number, and I've got that connected to pin 27, and we pass that in. and then the frequency, and I forget exactly what that 0.5 is. It evades me now what that is. But at the end here, we pass in a true, and that puts it into this high precision mode. If you don't pass that in, then you get a really jerky response, which sort of just demonstrates how difficult it is to do timing on a Pi. So this sort of abstracts away some of the operating system and dives under that to be able to get more advanced timing. Once you've created that PWM channel, though, you can just pass it straight into a normal servo motor from the device bindings, and off you go. And I've used slightly different figures here from when I was messing around, but I'm pretty sure it makes no difference for what I was doing. Next up, we start the servo motors up. So that just assigns the pins, gets them all set up, and the PWM starting essentially. Now, what I've got down at the bottom here is a tiny little routine that I use a little bit more later. But for now, all it does is it takes in a servo and an angle, and it writes to that servo the angle you want to move to, and then it just stays there. So I've got a bunch of these. So I say servo motor 1 start at 70, and then you can see down here on line 52, I move it to 150. Servo motor 2 start at 20, and then on line 54, I move that to 50, and then servo motor 3 will start at 80, and then it will move to 150. So we've got the rotation, the reach, and the grab doing a little dance there. And at the end, I'll just stop those servo motors. What that does is when you stop it, it means you can actually move it. If you've left it in a funny position, you can just zip it back into the place where it should be. So let's run that up and get our, there we are, back on the screen. I'll maximize that again. Point this back this way a bit so you can see the arm. There we go. There you are. So now it's moved, and you can see it will do a little dance. You see the last one being the gripper, and then the reach back there, second one, and then yeah. So that's us controlling the servos. So essentially controlling a robot arm with .NET at that point. Can you use Lego Mindstorm servos? Possibly. I haven't tried that. And will it work on a Pi Zero? And Alistair is quite right. The Pi Zero is ARM6. It doesn't work with .NET. You need ARM7 only. There's a set of extra functions in ARM7 that they rely on for .NET, sadly. So no Pi Zero, no Pi 2 either, I don't think. I think you run a Pi 3 onwards. I think Pi 2 actually has got something wrong with the .NET implementation that stops it from working as well anyway. So yes, Pi 4 is by far the best experience because you use a Pi 3 and it's just slow, apart from anything. So yeah, that all seems to be working. So happy enough with that. So I can stop that now. And that's great. That makes sounds if you don't give it a little tap every now and again. But there's no interactivity here. And I looked at this code, and if anybody's watched any of my talks before, I'm nearly always talking about things like IoT Hub. And of course, we could do stuff with IoT Hub here, but it's not really meant for what I wanted to do. What I wanted to be able to do was move the robot arm around. Yeah, there's no. I think it does threading, but I don't think it uses all 4 of the cores. I think that's what it is. So you can certainly do async await, but it won't do multi-core stuff properly on each core, sadly. I think maybe it's possible the very latest version of .NET 5 does, but the last time I looked, it didn't. It was just single chord. So yeah, threading works, but in a single core, which is kind of cheating, really, if you ask me these days, being as it's a quad-core device, you know. So yeah, as I say, I wanted to be able to control the robot arm, move it around in real time. And I thought maybe a Blazor app would be the best way to do that. So if I go back to my slides here, then we can talk a little bit about Blazor. So this is a single page framework for building client-side .NET apps for the web. It actually started life as a pet project of this guy, Steve Sanderson. He created it and he demoed it at a conference, and some folks from Microsoft saw it and jumped on it. And ever since then, it's gone from strength to strength. It's an awesome way to be able to do away with JavaScript, or for the most part anyway, as it's all in C#. So no more JavaScript there. It's going to be loosely abstracted away from ASP.NET. So you're still going to be using Razor and HTML for that. So it should feel familiar. And we have a few different options, and the two main ones are server-side or client-side WebAssembly. So server-side will sit there on the server, if you will, and a little thin client will run on the browser, and it'll receive the DOM changes directly from the server. So actually, this is pretty good if you want to make sure your code doesn't get leaked out to the public, because it's just going to sit there on the server, and all you're going to get is the HTML bits and bobs coming down. Actually, it uses something called SignalR to be able to orchestrate these changes, and it works really well. I think you can get many thousands of people connected, many thousands of simultaneous connections without it slowing down. And if it does, then you can just boost up your server or spin up more and load balance and things like that. But the part I was interested in was client-side WebAssembly, so that's where I went to. And this is obviously WebAssembly. If you've not heard of that, it's just a way of being able to run like .NET in a virtual machine, if you will. And if it's fully supported across all major browsers now. And actually, it runs full .NET standard in the browser there with no plugins. So it's not Silverlight. This thing is proper .NET, and if you were to look at the code and look at the network, actually, then you'll see it pull down DLLs and run them directly. It's not using bytecode yet, so it's not assembling it, if you will, and that's coming if not already there somewhere. So it's great, and as I say, supported in most modern browsers. But Blazor is only half of the story. We need some way to be able to communicate between the browser and our robot arm. So I wanted real time. I didn't want to have any wait. I wanted, almost lagless control of my robot arm. So SignalR is what we want for that. And this is a ASP.NET library that allows us to be able to create real-time communications between points for .NET, which is great. So this is open source, created by these two clever folks, David Fowler and Damien Edwards, way back in 2011. So this is a decade-old technology now, well-tested, well-proven, and enables us bi-directional communications between 2 points. I'm only really interested in unidirectional communications. I want to control my robot arm from the Blazor app, but you'll see we can make use of that in a bit. It supports at the top level WebSockets, which is going to be the best way, but if it can't find a way to use that, it has this facility to drop down to server-side events and even long polling if it can't get that to work. So let us drive the arm with our Blazor and SignalR app. So if I switch over to this one, just here in fact, and I get my code up on the screen. I'll briefly talk through the code here. So I've actually got this running, and if I drag that onto this side of the screen, for now, that will do. Then all I've got at the moment is 3 sliders for my robot arm controls for the servo. So we've got the rotation at the top, the reach there in the middle, and then the gripper there at the bottom. So if I just make this a little bit smaller, it's going to be a case of balancing windows together here. In fact, let's do it this way around. Stick that one there to the left. So I get the code back up again, and we hide that out of the way. I don't want to close it for now. So there's a few things that you need to do to get SignalR embedded into your application, and one of them is that you need to add it in as a service in here, and you also need to map it as a chat hub. So we've got in here we've got the mapping, and that maps to this chat hub file, and all the chat hub file is doing is receiving a message from somewhere, from a user containing a message, and then when it receives that, it sends it back out to everybody. So everybody that's connected will receive this message. And if I look at my index page here, and again, I won't go into too much detail on this, but I've got 3 blocks here, one for each of my sliders, and they are linked up to some properties down here. There we are. So there are my properties, Servo 1. And when it changes, I send a message out to that send message function. So that's how it knows on that. And I pass in the servo number as the user. If you've ever done any SignalR, then the first thing you're going to do is a chat app. And this is essentially a usurped version of that. So the message that my user, my servo, is passing in there is just the servo value converted to a string. And I've got 3 of those, 1 for each servo. And up here, when my page initializes, I create a connection to my SignalR hub, which for this particular server is just sitting on Chat Hub, which is great. That's how that's working. And when I receive a message, I'm going to stick it onto the screen. So if I get both of those on the screen again there, then at the bottom here, you'll start seeing those messages, I think, appearing at the bottom. So that's the basics of that one. Now, I'm just going to make sure that I've stopped this application, and I have. I can switch to my code. And in fact, let's do right up to main on here. No more switching of code anymore. What I've done is I've added in SignalR into my application here, and just like in this Blazor app there, I've got a hub connection, and I'm still spinning up my servo motors. I'm still starting them, but here I am creating a new connection, and I'm passing in the address of my machine here. So, of course, this code is going to run on the Raspberry Pi. So it needs to know the IP address of my machine that I'm presenting to you from here, which is running that little web server. And it's got a port that it's running on, 5001, and I'm just passing in that same Chat Hub address to tell it where it needs to go. Now, one thing I did find that I had to do, and I've just not had time to try and solve this, is that I couldn't get the Raspberry Pi to trust the certificate on my PC. And I tried a bunch of stuff, and some people said you can refresh the certificates, clear certificate stores, and I tried a bunch of stuff, and I just got bored of doing that. And I found that you could do this little line here, and you could tell it it's really dangerous, as it says, to accept any certificate. Do not do this in production. Find your way around this problem. But for me, this works perfectly fine for a demo. The other thing I've added in here is that we ask it to automatically reconnect. Just in case the connection drops, it can then automatically reconnect itself, and you're none the wiser. Then we build that connection. And then over here now, we use that connection, the SignalR hub connection, and we look for receive message. And if I switch back to the code in the Chat Hub, you'll see that we're sending out a message of receive message. The nomenclature is a little bit confusing, but it makes sense when you see it in the code. And we're expecting a user and a message. So each servo, when it's moved in that slider, when it's moved, will pass in its user, which will be servo 1, 2, or 3. And then its message will be the angle we want to move it to. So I convert that to an int32, and then I'm just using a case statement here, essentially an if statement, to be able to choose which of these 3 servos I'm going to be moving. Many different ways we could have done that, but this one works. And then I write that out. So that kind of makes my code down here just a little bit simpler to run with. That's the only reason why I've done this. And then again, at the bottom, I stop those servo motors. So if I run my code up there, then you'll be able to see that running. And this is where we have to have many things on the screen at the same time. So let's let that finish running. Don't worry about that unreachable code. I can hear that my robot arm has started. Now, if I move this, then we can see we're now rotating that robot arm. And then I can reach. And then I can play with the gripper as well. And you can see actually, although it looks like it's jerky, it's actually very smooth. I think you'll probably find it's just the connection on Zoom that's making it look a little bit not. But that's impressively smooth for saying that timing is done in software. And it was only relatively recently that I figured out how to do that with some help from the folks over in the .NET team with that. So yeah, that is me controlling my robot arm using Blazor and SignalR. But wait, that isn't everything. Now, if I go back across to here, normally at this point I will demo the way to do Uno, but I'm going to talk about it and not demo it, because every time I try and demo it, my machine is just not powerful enough to do Zoom and pretty much anything else. and certainly not remote deploy an Uno project down onto a Raspberry Pi. There is a video of that out on the YouTube there if you wanted to go and find that. But I will talk about Uno Platform because it's fantastic. So Uno Platform is a way to be able to run UWP apps on a Raspberry Pi. Now, if you've ever done any sort of Linux graphical programming, then you'll know that you're going to be stuck not using something as nice as XAML. I forget now actually what the name of the technology is that you'd be using under that. GTK, in fact, my last bit on the next slide explains that. But this is allowing us to be able to use UWP, which is XAML markup, and C# to be able to write graphical applications for the Raspberry Pi. And it works really well. It's created by Jérôme Laban, and actually he does live coding with his Uno platform every Tuesday. It's well worth checking that out on Twitch. This is open source and cross-platform, and they're involved with the .NET Foundation as well. So they're doing good things with Microsoft there too. They're on Uno Platform 3.something. I think 3.0 was released at UnoConf about a year and a bit ago. And it uses WinUI 3 as well, so we get some of that goodness. Under the hood, it's using Skia and GTK to be able to transliterate the XAML stuff into something that works with the Raspberry Pi. And I would demo it, but again, it's just too much of a complication. Now, before I move on to that next part, once we've got our little application running here, which is fantastic, we can actually branch this out. Now, myself and Liam Gulliver have got a slightly different version of this talk where we talk about DevOps. And one of the easiest things to demo in DevOps is web apps in Azure. So we deployed this same app to Azure. So if I just close this one out so we don't get too confused, and I stop my application from running, what I can do is, if I switch the address for this to something else, so let me just get the notepad open and find out what that address was. This one here. I'm just going to change that to this. Hello, you're going to do it for me. There we are. Drink. And if I run that up, this is going to do a very similar thing. Let that finish running. What's wrong with you? What did I do? Do that again. What's he complaining about? Type of hub connection, but and I know why. Because when I pasted it, it must have pasted it in somewhere else. There we are. Pasted it in somewhere else. There we are. That's better. Let's try that. It pasted it right into the middle of the hub connection builder. Oh yeah, there we go. Copy and paste error. Thank you. There. Let's try that one, shall we? Well spotted. Pair programming, you see. Yeah, there is a reason for that. It's good. Do that again. Yeah, I can hear that starting. Now, if I switch to the next screen, what I've got here is a web app version of that same app running. And you can see tiny little version of that app. Oh, it's fallen over a little bit. It's got caught. That's what the problem is. There we are. It's reaching too far. There we are. So turn that round. And this is still using SignalR. But if I paste this into the chat, then you can go to that address now, and you too can control the robot arm remotely. Now, first time I demoed this, one of our good friends from the .NET community had just moved to New Zealand, and he was able to control this from the other side of the world in near real time. It was dead good. It worked really well. So what I tend to find what happens at this particular moment in time is that people go crazy with it and move it all over the place. Now, when I built this thing, this robot arm, 3D printed robot arm, the 3D printed parts designs are in the GitHub repo, so you can print it yourself. But what I found is that I forgot to put a screw in the base, and so the whole thing falls over every now and again, which is quite embarrassing. But you can see when you move it, it says please wait in that particular servo. So one person can control one servo only, just to stop that contention. But other people could be moving one of the other servos at the same time, which is great. I like that. But still, we are not finished. I go back to my slides. Now that we have SignalR, we can do something even more fancy. And we can start looking at VR. So Unity is a cross-platform game engine. And if you didn't realize, founded in 2002 by Nicholas Francis, Joachim Ante, and David Helgeson. This is a cross-platform development platform that you can deploy onto lots of different platforms, including VR headsets. And it's all written in C#. And now that we have C#, we also have access to SignalR. So I thought, well, this would be great. I've just bought myself an Oculus Quest headset. Let's see if I can control my robot arm using an Oculus Quest. And I can. So if I switch across to the very end tab over here and get this open. Now, this part sometimes works and sometimes doesn't because, this is always one step too far. But what I have here is my trusty Oculus Quest. And if I get the thing up and running, and let it find my Guardian, because it can't find that. There we are, it's found me. And get my apps. Just bear with me a second. I'll just get the application running, and then I will cast, and you'll be able to see what I'm doing. Oh, everybody stopped controlling the robot arms. Either it's broken or you literally have stopped. Oh no, yeah, it's still working. So if I then do this and then cast, and then I cast to my computer, hopefully we will have, there we are. So you should be able to see that working. It's a bit slow and jerky at the minute. I'll just make sure that I've got enough power assigned to my machine. Give it some more of that. There we are. Right, I might need to do that again. Let's do that again. Stop casting. You can do it. Right, let's try this. F5 into that. This is it's always a little bit quirky because I'm trying to do quite a lot with the machine at this point, and it struggles. It won't stop casting. Blooming thing. Ah, there we are. That's doing that. Right, let's go back into this. Nothing's ever fast when you're demoing it. Right, and then cast that. Cast. Computer. Next. Come on, you can do it. Right, so you should be able to see that on the screen. It might be a little bit off the bottom, but you should be able to see that. Now, if somebody moves the robot arm for me in the app, there you go. Oh, look, my robot arm is moving in the app in real time. So this is like a little, VR representation of that robot arm. And likewise, I can move the rotation. It's probably got stuck again. It has, oh well. Because the reach is a little bit too far up. But if you move the grab, you should see, oh, look at that, it's fallen over. If you move the grab for me, then you should see that little pincer going up and down as well. So the third servo in your thing, there we are, look. So you can see that even moving around and the reach and everything. So we've got two-way communications between a VR app and a real robot arm sitting on here that you can control from practically anywhere in the world. Now, I know it's sort of wobbly and it looks a bit silly and, may not immediately seem like it's got any uses, but essentially it has. I mean, this is a similar sort of idea to medical robots that have been able to be controlled by doctors on the other side of the planet. And I think there's an advert for EE even at the moment where you've got, who is it, Richard Bacon or somebody like that, Kevin Bacon, him, shaving somebody on the top of a mountain. But the idea is the same nonetheless. So, I was pretty happy with myself when I got it to do all of that. So, yeah. So that was VR robots. And that is essentially the end of my talk. So there's a bunch of links here, which you can go ahead and check out. Don't worry about copying all that lot down. There's also, I also run a Twitch show called IoT Live with Cliff Aegis. It's worth checking that out. If you're interested in sort of upskilling your IoT, then I've created, along with a few other authors, a Pluralsight course to help you pass the Microsoft Azure AZ220 IoT exam. So by all means, go and check that out. And if you're really interested and you don't have a Pluralsight subscription, then drop me a line and I can help you out with a 30-day all-access pass to Pluralsight for that. If you want to contact me, then any one of these places are great, but Twitter I tend to find works best for me. And the slides link there is available for you. You can go and grab that now. I realise I've actually loaded up essentially the wrong version of my slides, because there's a nice little part at the end. Let me just get that. Let me just get that one. Where is it? Disappear from there. I'll start it from that next one. Here, I've got a little blooper reel from when I was creating this. And my cat decided that it really liked the sound of these servos. So the cat would get involved and start, why is that not playing? Come on, you can do it. Let's go back and on again. There we are. So she'd get involved and knock this thing around, which, you know, was interesting until you're trying to work that way. The other thing is it can be really jerky. So this is what I was showing you. If you don't use that software PWM correctly, it gets really jerky. And if you don't fasten it down properly and it's really jerky, then it, you know, doesn't last very long. So, so yeah, that's the basics of that. So do go and check all of them slides out there. And other than that, thank you very much for watching, and you know, do get in touch if you need me for anything. So yeah, so that's that. So thanks for watching.